Okay, let's press on. So I thought I'd draw this diagram because it got a couple of questions during the break that kind of suggested people weren't entirely sure what was going on. And drawing diagrams is the only way to understand all this stuff. So if you've got a bit of paper, scribble a diagram of what you think the data structure looks like. Alright, so we've got this stack underscore t object, which if you remember is simply a pointer to a struct stack. Here's a struct stack. It contains three components. One is a pointer to an array, the other one is the size, which tells you how many items there are in the array, and the third component is the index of the next place where you can push an item into the array, exactly the same as with the original static array size. So you can see from this diagram that the array itself is outside the struct. It's not contained in it like it was up here. So this whole thing here is the stack struct, or struct stack if you want. Here, this is the struct stack, and this is outside. And the reason it's outside is because we want to be able to fiddle with its size, and you can't do that if it's built into the struct. Alright, so keep that in mind while we're talking about how things work. Alright, now let's go back here and have a look at push. So I'll take this over to the realloc version. Let's see where that's going to end up like. Alright, so pushing an item onto the stack. So we've got an array, we've got an index that tells us where the next place in the stack is to put an item, and if we've got a fixed size array, that's what we do. And in fact, if we did nothing else, if we simply allocated the stack, allocated the array once at the start, then this code would still apply. However, that's not what we want to do. What we actually want to do is we want to be able to change the size of the array if we discover that we filled it up. Right. So first thing to check is, how do we know it's full? Well, we know it's full if that condition is true, because remember, top tells you, it either gives you the index of the next place to push an item, or it gives you a counter of the number of items that are currently in the array. Size tells you how big the array is. So if the number of items in the array is the same as the size of the array, it's full. And the push isn't going to work. So we could easily just say that and give up, but we don't want to do that. What we want to do is we want to change the size of the array. Now you might say, how do you do that? And see, well, one way you could do it is you could allocate a new array that was bigger than the existing one, and then copy all of the values across, and then deallocate, then free up the original array. That would certainly work. But it turns out that the C library has a nice little function. You can always check these things up by looking in the manual. The reason I'm using 3 here is that the manual, the Unix programmer's manual, comes in a number of sections. Section 1 is all of the commands like cat, ls, gedit, and so on. Section 2 is system calls, which we haven't talked about at all. If you do COMP1511, you'll hear all about them. And section 3 is all the libraries, like standard IO, blah, blah, blah. So realloc happens to be in one of the libraries, and it happens to be in the library that also defines malloc and free. And there's another function called calloc. Calloc, you could use that if you want to allocate something and you want to make sure that it's full of zeros. So calloc basically is malloc plus clear the whole array out, or clear alloc if you like. So malloc allocates a bit of space, free tells the system that space is no longer in use. Realloc takes an existing object and says, I want to have a new version of this object that's this size. Now in theory you can make it smaller. In this context that would be not a sensible thing to do. But what realloc returns is a pointer to the new object. Now there's a little bit of trickiness going on behind. Realloc will make sure that the new object contains all of the values that were in the original object, and it will make sure that the object is bigger. Right? So if you had an object here and that was full, and you do a realloc, you're going to get a new object that contains all of the values up to there, but there's this much more space that you can start using. Now with realloc, it understands how the memory allocator works, and if you don't understand how the memory allocator works, do COMP1511 and then you will. But because realloc understands what's going on underneath, it can say, all right, here's this space that's been allocated. The user's just asked me to make a larger amount of space available. I can check here, and if that's free space, then I can simply reallocate the thing in place. But if I've got some allocated space here and there's another object that's been allocated here, obviously I can't just extend over the top of that. So I'm actually going to create a new object, copy all the data across, and then return a pointer to the new object and free up the old object. So it does all that work for you. So here we could just call realloc, and the reason I wanted to look is I never remember what the arguments are. So you've got to say what the current object is, and you've got to say how large do you want the new object to be. Where are we? Oh, it was just here, wasn't it? Alright, so if it's too big, then what we want to do is we want to make the elements array bigger. And so we need to know where the current elements array is, so we've got to pass that as a parameter. And the second parameter is how big we want the new array to be. And that we have to make a decision. And in fact, we probably should have made that decision in advance. So let's say, for the sake of argument, we could increase it by 50%, or we could be pessimistic and say, well, if the user's stuck this many elements in the array, maybe they're going to want to stick twice as many elements in the array. So we can just double it. Memory's cheap nowadays, so it doesn't hurt to allocate too much space. Alright, so we need to tell we need to indicate inside the stack struct how large the array is, so we can do that there. And then we need to allocate or make sure that the array is that size. Yeah, this is slightly annoying. Maybe I'll put that on another line. Still not going to fit. I don't want to have wrapping that's annoying, so I'll just have to break it up and make it look a bit funny. Alright, so how much space do we want the new array to have? Well, we just decided how much space or how many elements we wanted to have in it. Stack size, it tells you number of elements, not the number of bytes. So we want stack size ints. So what's going on here? Look at elements. If I can, extend it to make it that big, which is twice as big as it used to be, and all the data's still there. Otherwise, make a brand new object somewhere else in memory. We don't care. and make sure all of the values from this object are copied into the new object, and then that becomes the new array. Okay. So if you wanted to, try and look at it diagrammatically, what's happening is, let's just get that out of the way. Let's see if I can. Sometimes hard to grab these objects. Oh yeah, gone mad. So what realloc effectively does is it says, all right, here's this 63-byte array. I'm going to make a new 128-byte array. So I'm going to use an old 64-element array. I'm going to make a new 128-element array. So the last index is 127, and then I'm going to make that the new array, and in fact it also gets rid of that at the same time. Okay, so that's what's happening with realloc, and you've got to imagine that there's twice as many dots in the bottom one as there are in the top one. So all of the data is copied across, but the object is twice as big as it used to be. So all of that changes on that diagram is being caused by that particular statement there. Right, so reallocate the space, give it to this new object. Let me see, what else do we need to do at this point? Probably nothing. The only way this could go wrong would be if stack size was equal to 0, but that's never going to happen. And then, in this scenario, we had to make the array bigger. In any other scenario, the array wasn't full, so there was space to put something into it. So, regardless of which scenario happened, by the time we reach this point, then the array is big enough to hold another element. So we simply put that element into the appropriate place in the array, and then increment the top pointer. Okay, so that's it. Realloc. Questions on that? Oh, actually, I had a diagram for realloc. Maybe I'll show you. All right, so here, take it out of the context of the stack struct. I could effectively create an array of 4 ints by doing this, and make those 2 assignments, and that's the scenario I'd end up with. If I subsequently do this, so take the elements array, make it twice as big, or give me an array that's twice as big, then I'd end up with this scenario. So I've got 8 ints in an array. The first 2 are the same values as what I had here, and the elements variable is now pointing at that new array. Okay, so that's what realloc's doing. Is that alright? Ooh dear. I'm getting confused looks. Pointer to an int. I malloc 4 ints and make this variable here point to them. And then I assign, oh yeah, so here's a nice example of, so elms, if you want the data type of elms, maybe that's what's confusing, it's an int star. Okay, so pointer to an integer, it happens to be a pointer to the first integer in a chunk of memory that I'm going to treat like an array. And then I can start treating it like an array. elm0 is that int object there, and I assign the value 4 to it. this object, elms1, is that int object there, and I assign the value 7 to it. Alright, for some reason I then decide that array is not big enough, I want to make it twice as big, so I allocate 8 integers, space for 8 integers, using the values that are currently stored here, and then make the elms int star point to the new twice as large object. And at the same time, all of the values that were in the old object are copied across, including, I would guess, the junk values that were here that I'd never actually initialized. And you get more junk added on the end. So all of these items in the elements array don't contain anything interesting. Only these two do. Plausible? No. Alright, go away and think about that. In the context of the stack, basically what it means is I start with an array of a certain size. If that fills up, I double the size of the array. That's the takeaway message from that realloc. Now, does it actually work? Let's see. I think stack 3 is that one. No, it doesn't work. Why doesn't it work? Because I suddenly decided to use GCC. Interesting. See, you can see a difference between GCC and DCC. Let me just change back to DCC. Alright, so now it's happy. Ooh. I wonder if it's going to work. Well, most of it should work because I just copied and pasted from the original array implementation, which we'd already checked and we knew was working. So really the only new thing here is the realloc section. Now in fact we're not going to trigger that unless we insert 64 items into the array. That's going to be a bit painful, so let's start out with just 4. So it's easy enough, we can push, and then if it's going to work, it should have doubled the size of the array. But there's nothing in the interface that allows us to examine the size of the array, so we won't be able to check unless I wanted to add a new function to tell us that. But as long as it works, and as long as I can keep inserting stuff in. I'll just test it. So remake. Alright, let's see. So push 3, push 2, push 4, push 1. Now the stack's full. If it's going to go wrong anywhere, it's going to go wrong on the next push. Beautiful. So the array got twice as big, so I managed to push an extra item into an array that was originally size 4. Tell you what I could do, actually, since I've got this show function, maybe I can print the value of size in that, so we can be convinced that the array has actually got larger. 4G array would take up a lot of space. No. Let's just add this. Okay. Whoa, what did I do wrong? Oh, that was trying to make stack 2, which I hadn't done as a complete program. Okay. Push 3, push 6, push 7. No, Notice the size of the array isn't changing, but the number of items that are actually stored in the array is. Alright, well let's hope. Good, okay, so the array just got twice as big. Oh, I'm so excited, I'm going to have another go at expanding it. That's true, we've only expanded it once, maybe it's only going to expand once and it'll break. And we try to expand again, bingo. Okay, so now it's 16. And if I kept pushing and I never popped, and this is one thing to notice here, that was something I was going to mention before. We filled up the array and we had to make it bigger, but when we take stuff out of the array, we don't reclaim any space. If we wanted to, I guess we could. You could add into pop. If the array fell below a certain threshold size, then you could shrink it. Doesn't matter. Memory's cheap. So then you say, why didn't you just make it a megabyte in the first place and then it would never fill up? Fatal mistake to say that. Eventually someone is going to write a program that's going to fill it up. Alright, so that's an implementation of stacks using arrays that can grow. So the original implementation's fixed size array, you fill it up, you're stuffed, you can't use your stack anymore unless you pop something. Linked lists, obviously linked lists can grow as large as you like, and similarly here we can reallocate the site, allocate a larger array using the realloc function. Now one other thing I wanted to mention is that let's just make clean. Oh, that's right. Damn. This is when I get lazy and jump into VI. Okay. One important thing to notice here is that in both cases I'm using exactly the same client program. So I'm using that main stack program, which is the thing that prints the prompt, prints stacks 1.9, blah, blah, blah. Exactly the same client, being able to use two completely different implementations of stacks because all it knows about, it doesn't know about the implementation, it just knows about the interface. So the nice thing about ADTs is because the user doesn't know about how things are implemented, they don't poke around and try to fiddle with the implementation. All they can do is use the interface that you've provided, and then as a programmer, you're free to change the implementation as much as you like. So if you decide a fixed size array is the best way to go, you can implement it like that. If some user comes along and blows it out, then you can change to a realloc array. Or you might decide, hey, you may as well go with a linked list straight away. Because that's generally, one thing about a linked list compared to the realloc array, the amount of memory consumed by the linked list is just as much as you need. Okay, with the array you've got extra space at the end that you haven't yet filled up. So you can make these choices without affecting users. Their programs will recompile as long as you don't change the interface, which is a really nice property of ADTs. Alright, let's, in the remaining time, take a look at queues. So stacks and queues are really simple data structures. They're both linear data structures, so they're basically a sequence of items. The difference between them is in the protocol for adding and removing items. So stacks, you keep stacking on top, and the only way you take off is the last thing that you put in. Queues work like a queue in a bank. The first person to reach to get in the queue is the first one who's served. The last one into the queue is the last one who's served. So it's basically first in, first out. First person in the queue, first out of the queue. Rather than pop and push, we've got operations that we typically call NQ and DQ. You can see they got the same kind of feel as pop and push, but the insertion and removal protocols are different. So here it's first in, first out. You can kind of think of queues as being like a variation on the list data structure, where the only way of getting stuff into the list is to use append. So if you remember, we had two functions for putting stuff into a linked list: insert, put it in at the start, and append, put it in at the end. So the only way we can get stuff into the queue is to append it, if you like. And the DQ operations basically take the front item off the list. Once again, like stacks, they're very simple data structure, but they're extremely useful in practice. Examples where you use them: simulations, very common thing. You want to simulate queues in a bank, for example. You know, find out what's the average queue length going to be. If I have this number of tellers and the expected arrival rate of customers is blah blah blah, you can write a little simulation using queues and see what happens. Queues very commonly used in contexts like operating systems. So if you've ever tried to print something on one of the shared printers on level 3, someone else might have printed something before you, so their printout comes out before yours. So there's obviously a queue involved there. Alright, so implementation wise, let's have a look. So I've implemented a little main program just like stk.c, que.c, basically prints out queues 1.9 and then allows you to enqueue stuff and allows you to dequeue stuff. Right. Probably, obviously I copied this from STK. You can't dequeue. I can leave it as popped. No, let's change it to served or something. So what other operations have we got? So enqueuing, dequeuing, check out who's at the front of the queue. It's when the back teller can decide to go to lunch if they don't like the look of the person on the front. Check out whether the queue's empty so you can go home. Check out how long the queue is, and so on. Alright, one thing you might notice about all the function names here is they're now prefixed by Q underscore. And that's important because if I didn't, and I tried to use stacks and queues in the same main program, I'd have name clashes. Because I had a front for stacks, I think it was called top actually, but certainly there was an isEmpty function for stacks. So if I also have an isEmpty function for queues, and it's called the same thing, how does the linker know which one I'm talking about? So it's very common with ADTs to, as far as naming conventions go, to prepend all of the functions in the ADT with the name of the ADT itself. So I know this is the isEmpty function for queues, or this is the isEmpty function for stacks, or this is the create function for queues. So I didn't do that with stacks, but if we were eventually going to use them in a common context, then it might be worth doing that. To run through and call stack underscore create blah blah blah. Alright, so the usage is pretty much the same as stacks. Let me see, do I actually have a compiled version of queues? No, I don't. Can I make because I haven't finished the implementation. Right, that's what we're going to do now. Okay, so we need to implement queues. So we'll start out doing them as arrays. It's interesting because stacks and queues, they look kind of, similar level of complexity. You're just sticking stuff in, taking stuff out. There's probably going to be an index that tells you where things go in and out. But it turns out queues are a little bit more complicated than stacks when it comes to implementing them. If you implement them as lists, they actually turn out to be less complicated. And that's another interesting thing about abstract data types, or the implementation of them, that often you can get very nice implementation using one particular data type for one ADT, or using a particular data structure for an ADT, and a very similar looking ADT turns out to work much better with a totally different data structure. So anyway, let's take a look at queues as arrays. Right, so this is a fixed size array. We'll stick with that for the time being. But the interesting twist here is that we need indexing that goes circular. And the reason we need that, let's take a look at the diagram. Where's my queues? Queues as arrays. Okay, so I guess there's a different way we could have done this, but the way that we're actually going to do it is that we've still got our array of elements, and elements are added into the array. They're added at the tail of the queue, and because we're taking stuff from a different part of the array, whereas with stacks we simply had, all we needed was a top variable and it was serving kind of two purposes. It was telling us where we could add stuff into the array. We were also using it to work out where to take stuff off the array, top -1, and we were also using it as a counter. In the context of queues, it's much simpler if we separate out those three functions. So we need to know where the first item is, so that when we do a dequeue, we can go to that item. We need to know where the last one is, because they're not in the same place now. And it's useful, for reasons that you'll see in a moment, to know how many items are actually in the queue. Alright, so here we've got an example where we enqueued 7, we enqueued 5, we enqueued 4, we enqueued 9, and then we dequeued 7. So we took 7 off the front of the queue. So the first item in the queue is now 5. It used to be this one, and that's at index 1. The last item in the queue is at index 3, that's 9, and there happen to be 3 items in the queue. And you might say, hey, we could have worked that out anyway, simply by taking 3 minus 1 and adding 1. That's true, and that works all right while we're moving through the queue the first time. But if we just keep advancing first and last, eventually we're going to reach a point where maybe first is here and last is somewhere around here. So what's going to have to happen is that first and last go along, they go to the end of the queue, and then they wrap back to the start of the queue. This is assuming that you've dequeued stuff on the way so that there is now space at the start of the queue. We can have a problem here that the queue fills up, the array fills up, so we end up we can't insert. So we've got first and last moving along the queue. I should move them in that direction for you, and then wrapping around and moving through the queue again. So first is always a few places ahead of last, and how many places ahead of last it is we store in the size object. So that's giving you a big fat hint about how to implement queues as arrays. So let's look at the data structures for doing that. Pretty straightforward, except that I called them front and back rather than first and last. Silly me. I could change the names, maybe I will. I don't know which makes more sense. And it was called size, wasn't it? No, I'll just leave it as front, that's right. I'll leave it as front and back. So the diagram had different naming convention. And the length of the queue, okay, just the number of items, the number of active items currently in the array. All right, so I'm not going to bother with the search this time. I'm going to cheat and say this. And if the queue that you're passing in isn't valid, if it's got a null value, then the whole thing's just going to fall over. So I won't bother with the asserts. However, I got sick of saying if blah blah blah, then f(f) exit, so I decided to package that up into a function. You'll see why in a minute. It's a function that's not going to be used outside this file, so I've defined it as static. I mentioned that last week, I think. Yeah, when we were dealing with linked lists, we had the function to create a new node. That was not relevant for users, so we defined it as, if you like, a private function on this. So this fatal function is private as well. Okay, so to create a new queue, once again we need to malloc one of these queue structs. In this case, the elements array is part of the struct, so we're using a static array which is actually contained in the struct. So when we do this malloc, it allocates the whole array plus the other 3 items that are part of the queue. If it fails, then we want to give up, and now I've taken the nice, possibly non-standard approach to formatting, but I think this kind of way of handling errors, where you simply have the check and have the let's get out of here thing all under one line, is quite a reasonable thing to do. So check whether new is null and then abandon the program after printing this message. Alright, so what else do we need to do? So we've allocated an array. We're not going to store anything in it. It's full of junk. It doesn't matter as long as we never access the junk. And we also need to initialize first, last, and I actually used the names from the diagram. Alright. We initialize them all to 0. The reason why the front and the back can be the same is that it's fine because we know that the length of the queue is 0, so we're never going to try and get something out of front if the length of the queue is 0. Alright, freeing a queue is as simple as doing free of the struct, because the struct contains the array. Adding an item onto a queue. Alright, in this case, we can't add something onto a queue once the array is filled with active items. So we make that check first of all. Adding something into a queue is relatively straightforward. You want to add it to the next available slot. Now remember, with a stack, that top index always told us where we could insert the next item. In this context, the back of the queue tells us where the last item is located. And did I call it front? What did I call these things? Front, back, and length. Yeah. Alright, so I need to change that. So the back queue arrow back tells us where was the last item that was added to the queue. So if I'm going to add another item, I have to move back forward by 1, and then because I'm adding something, I obviously increase the length. Okay? And then because queue back is pointing at the last thing that was added, or it's an index to the last thing that was added, that's the index I use into the elements array, and that's where I store the item. So that's the enqueue operation. For the time being. The DQ operation is kind of similar, but in this case we can't DQ if the length is 0, because there's nothing to take out of the queue. So that's a fatal error if we ever call DQ when the queue is empty. So I'll just do that. Alright, so to DQ something, we basically take the item off the front of the queue. Let me see. Okay, here I'm going to do what Andrew did, which I thought was a bit naughty, but he used a plus in the middle of an expression. So we have to increment front, we have to decrement length, and we have to take out the item that's currently at the front. Alright, so one way of doing that is to start by decrementing the length. Okay, there's one less object in the queue because we're taking one out. And then we want to, and as I type this I'm thinking this is a bad idea, so I won't do that. It's too confusing. So we're going to grab the value that we're going to return. And so that's the thing that eventually gets returned. Which value are we returning? We're returning the one that's currently at the front of the queue. That one there. And then we need to increment front. And decrement length because we just took something out of the queue. Right? Hopefully that's reasonably straightforward, and I hope by now you are getting reasonably comfortable with expressions like that. I'm sure at first sight you go, what? But we've looked at that kind of thing a few times now. So queue elements is an array contained in a struct queue object that the variable queue is pointing at, and we're indexing into the array using that component of the queue object that the queue variable is pointing at. Right, and queue size equals 0, queue is empty, that's pretty straightforward. Queue front, if the queue is null, alright, that was effectively the assert thing. Queue front, we basically just take the element at the front of the queue, so that one's easy. So the element at the front of the queue obviously is in the array, and it's indexed by front. And the other thing we need to do here, of course, is to check if someone asks you for the front of an empty queue, then you ought to complain at them.
Is it length or size?
Yeah, thanks. Yes, it's like, oh, I had that above as well. Oh.
I think you also didn't do that in
Yeah. Alright. That'll do. Pick a short error message. Where was it? Length? Oh.
queue, a little bit above.
Yeah. Oh, yeah. Is that it?
Yeah.
Yep. Alright, well it's getting late, so we'll take a look at the rest of that next week. So the thing I haven't done is implemented the circular indexing. So at the moment, these things just add, queue front just keeps moving forward. I'm not checking whether it's reached the end of the array, so it's just going to keep adding and adding and adding and fall off the end of the array. So I'll show you how to deal with that next time. Okay.